然后那个档案，这个档案在
第六章这两边，然后
一个档案 ，OK，OK，这是我那个范例嘛，哈。
对。
好，所以你刚才没开，都还没开。哦，
那我另外开。
不用，没有，我再开就好了，
好
完成我再开就好了。
OK，那是这一
本。好 ，OK， 我来找我看。好，谢谢。还是这个。Okay, so let's continue our previous optimization problem. So generally, if you face your problem is unconstrained, it's very easy. You just take a derivative and take it equal to 0. Like previous, we use this example. It's an unconstrained optimization problem. So if you have the function, just take the derivative respect to all the parameters in your equation. So how many parameters you are going to make your final decision to make your function become objective function become the optima. So take the derivative equal to 0 and and then solve the equation over there. In this condition, we say this example we can see it's just easy to derivative to two variable equal to 0 and solve the linear equation, and you will see the result for the best parameter combination for this function. And the second condition is some constraint optimization problem. So which means you have your objective function and constraint to some certain condition. So for example, like this example, we have this box, and we try to maximize the volume, but we have some constraint condition to limit it satisfy this specific requirement. So for example, like this one, we want to the area, the surface area of this box is a square. So you have one more condition to consider and maximize this volume. So if you can try to summarize these two the objective function and your constraint and combine into one equation, it will simplify your approach, optimization approach. So we use this example to demonstrate. Actually, you can transform. If you can transform the unconstrained this condition into our objective function, so we will transform the unconstrained optimization into constraint, into unconstrained. Okay, constraints into unconstrained, it become easy. So you just like this example, it become 3 parameters. So this equation we can see. Okay, we combine it together, and you go back to unconstrained again. Take the derivative equal to 0 and solve this one. So I hope you already done this one by yourself. It's just some mathematic linear equation problems. But the second, we introduced a new one because our textbook DIP, digital image processing, use a lot of this kind of optimization problem. We use a Lagrange multiplier. So we combine these two issue, the object function and your constraint condition, and use one Lagrange multiplier to combine them together. For example, our question is the same. Okay, we have the volume. Okay, and we have this z equal to this the value you want to maximize, and subject to some specific constraint, like your surface equal to a squared surface area, and we use this Lagrange multiplier, this lambda, add up these two together, and then you have a new equation there. And again, so you can optimize this one by a derivative operation, the calculus, and then try to solve it, find out the result. So let's do this quickly for the previous example. So we have an example of maximize the V equal to XYZ, right? We try to minimize this issue. So later on, we are going to minimize some, for example, your smoothness of your image, and try to constrain to some condition subject to GXY equal to what? Equal to our constraint is 2xy plus yz plus xz equal to a squared, right? So let's combine this equation. So we have to subject to something equal to 0. So you know your constraint condition is 2xy plus 2yz plus 2xz minus a squared equal to 0. So that's our constraint. So we can write down this one, 2xy plus 2yz plus 2xz minus a squared equal to 0. So that's our GSY, some constraint condition there. So we just write up this Lagrange optimization approach. So your fxyz equal to what? Combine these two together. That's we mentioned fxy, your fxy plus lambda gxy, g of xy. And now we actually try to actually you can plus the positive Lagrange coefficient or negative, either way. Okay, but for easier representing in our result, we use this one Lagrange combination. We say we combine these two, xyz minus lambda. Actually, you can use plus lambda. It's okay. You can find the result later. Okay, but here use some minus lambda is easier to represent. Plus 2yz plus 2xz minus a squared. Okay, so we created a new combined Lagrange approach. So here we know we have this issue to solve where is the maximized result. So you have to do some partial derivative. Ln f ln x equal to 0. Ln f ln y equal to 0. And ln f ln z equal to 0. So let's see. Actually, it's pretty simple approach here. So please just take the derivative to x. So you can see the first equation become yz. Okay, 2x. So it become yz minus. So let's disappear. Only the item contain x parameter. It was remain the result. So it's 2 lambda. Like this one, derivative to x, it becomes 2y. 2y times lambda, it becomes 2 lambda y left. And this one, only 2z left. So you have a y plus z. And for this constant becomes 0. Okay, and this yz, derivative to x, it becomes 0 as well. So we have this yz equal to yz equal to 2 lambda y plus z. Again, this one derivative to y and equal to 0 for optimized location. So to y it becomes xz. And what else? Xz minus 2 to y. So it's 2 lambda to y is become x and plus z equal to 0. And this one derivative to z. So you have to z. So it's to z is what's the result here? Xy minus 2 lambda and what else? To z. So it's only y left here and x left here equal to 0. So you have 3 equations remain to solve. It's also a linear equation. Actually, you have this one. We can say this is the 1. This is the second equation. This is third equation. You are going to solve. So make it easier. So we can move in the second term to the right equal sign. That's the reason I use a minus lambda. So you can see here we can say it is one equal to this one equal to this one. Shift to the right hand side. So you have 3 equations, right? Yz equal to this one, blah blah blah. So why we do this one? Because we are going to use some trick there. So what's the trick? Maybe you can take the second equation divided by first equation, right hand side, left hand side. So you can see in the 2 divided by 1. So in the left hand side, the z will cancel out. So it becomes x divided by y equal to what? 2 lambda cancel out. So it's become only x plus z divided by y plus z here. Okay, so for this equation, we can see xy cross multiplication. So you can multiply this both sides. So you can derive xy plus xz equal to xy plus yz. So from here you can see cancel out because xyz cannot be 0, right? Your edge of the box. So it's cancel out. So and xz equal to yz. What's the result? Tell us. The result tells us x should be equal to y from this 2 equation. Your x, h of x and h of y should be equal. And we need another one, so you can take any two equation again. So maybe we take the third one divided by second one equation. So what can you get? the third one divided by second one. So the x will cancel out. So in left-hand side, we have a y divided by z equal to what? Right-hand side, 2 lambda also cancel out. So you have a y plus x divided by s plus z. So again, cross multiplication. So what can we get? Sy plus yz equal to yz plus xz. So yz cancel. So x cancel and y equal to z. So from this the second 2 equation, you can discover y should be equal to z. So which means x should be equal to y and y should be equal to z. So in our approach through this Lagrange multiplier analysis. So in this sense, you have x equal to y equal to z. So what does that mean? Your surface is 2 times xy plus yz plus xz equal to a squared. That's your constraint condition. And what's the result? So you know it should be x equal to y equal to z. So you 2 times 3x squared. If you all change to x, so equal to a squared, which means 6x squared equal to a squared. So x should be equal to a squared divided by 6, take the root. So equal to a divided root 6. So equal to y equal to z. So which means, just tell you there's another approach to solve your optimization problem. So we have an object function, try to minimize or maximize some specific target, and then constrain some conditions. If you cannot replace through this parameter change, and then replace into an unconstrained optimization problem, that's fine. We just combine together. Use some Lagrange multiplier. Okay, so this you change this lambda a little bit. And why we do this one? Because later on in your textbook, they didn't say anything. They suppose you already know the optimization techniques, and they just give you a result. Okay, so is that okay? So that's an approach for the Lagrange multiplier. So we use this simple item and then solve this issue unconstrained approach. Okay, so this is the way we do it. So you have this objective function, and then you have the subject to constrain this condition, and then you can use some Lagrange multiplier to combine this equation together and then solve it through the optimization approach, and you can find out the result. Okay, so we are using this later immediately. So this is also some brief review and the matrix differentiation. So you just know there's process for your vector differentiation, because later on we will see the result there. So for example, x is the vector, and f is a function of 2 variables, x1 and x2. And you are going to take the derivative to this vector, so we have to do this, it's become a current vector with respect to s1 parameter, s2 parameter, respective as a vector result. And we use this a lot. Okay, for this example, for this one, there's some, remember we transform our image processing. We have h convolve f plus eta, right, as our output observed image, right? This is a special domain. You have your convolution, you have the convolution operation through your original image, and then convolve with some blur function, okay, degraded function like a h is a motion blur, whatever, is a degraded function, and then add some eta. So this is kind of a basic image processing, but we can change it to like this one to represent it. Okay, plus eta vector, g vector, and this become a matrix. It's not convolution anymore. It's a matrix vector operation. We described this in previous one. So if we try to minimize, optimize this kind of problem, you will face a lot of vector derivative. Okay. The relation in calculus. So let's just tell you, if you have a vector matrix, this is A is matrix, right? X is the vector, B is the vector, just like this one. H is the n by n. So it's depend on your F. Okay, original image is a 1 dimension or 2 dimension. Okay, so H is succulent, Bloch succulent matrix. So let's just tell you the basic vector derivative will become like this one, because you have to take this like this transpose as a transpose to this a vector again. So get this matrix. So it's another one. So this one is just tell you the very traditional vector derivative regarding to your vector x1, x2, and we can see the result just similar. Okay, just similar. You have you have this one derivative this one to x, and what's that? 2x decrease 1 dimension, and then times if you have any vector any content. So similar. This is square, and this result is 2a because there's ax there. So the a will remain outside. So you can see this is the A is the matrix. So, but in here we have a transpose added for the matrix, and remain this whole vector again. So it's very similar to our traditional calculus. But remember, it's a matrix. So this just give you some idea of this one matrix vector operation here. Okay, so now we are going to see how we use this basic matrix differentiation and Lagrange multiplier to our system here. Okay, so let's recall the calculus we just mentioned for the Lagrange multiplier. So remember, our problem is try to minimize the QF here. So that's our issue. So our problem is try to minimize maybe your variance of your image. Okay, and this is our original degraded imaging system. Okay, remember we have what? We have G equal to HF plus eta. So your equation is G minus HF equal to eta, minus eta equal to 0. So we are going to combine your constraint condition there, adding some Lagrange multiplier. Alpha here is just we mentioned before is lambda. And this is your minimized objective function. Okay, so maybe minimize your variance of your image. And this is the new condition we are going to solve. Now you understand what this comes from. So we have a objective function, minimize something, and we have our constraint combines together through this Lagrange multiplier. So once you have this one, the second stage is try to derivative, apply the derivative to get the best optimal result. So we have to apply this one, run this one to run F. Okay, and you can see you take a derivative of this one we mentioned in previous operation for matrix derivative, and you have this result QF is become to move to in front, and Q transpose to Q. It's a matrix, and then take the QF left, right? QF remain, and the coefficient of the F is a Q, so we take out. So you have a Q transpose Q here. And for the second term derivative with respect to F, okay, to F. Okay, so what's the result? For this one, the first term, the alpha, the square, okay, square 2, you have to move to in front of that one, and the alpha, the same, the constant in front. And inside of this term, the G minus HF, only H is the coefficient of the F. So the H will be moved outside, and this term will be remain 1 times. Okay, the order of 1. So that's the result. And because this is minus, so it's a minus take outside. The root 2 to if you have a wrong minus a x to x. it become minus 8. So it's minus 10 there because it is minus 10. Okay, so take a close look. You have this result here and equal to 0. Okay, so the matrix here, operation, actually in your objective function and your constraint condition combined together with respect to f vector, your image. Okay, so we want to find out which one is the best condition. So you can see, take the derivative equal to 0. 0 is the optimized solution for this combined equation, and we get this result. So when you get this result, what's the person we want to solve f vector, the image. So you can combine together f and f hat together. F hat is your estimate result, right? Your target, your final purpose to find the f vector, the f image. So where's the f? Combine together the coefficient, and this one f have this term times this term. So you can see, 2 you can cancel out first because equal to 0. It becomes more simpler. Okay, the constant 2 can cancel out because equal to 0. So you can see for the f hat, they have the first term here. The second term is the minus times minus become alpha h transpose times h. So there's only coefficient combined for this f hat estimate image. And the other term is here. So move to the right hand side, equal to alpha h hat g. G is your observed image. So our final result will become like this one. So this is still matrix, right? So it's a matrix moved into the right hand side. So it becomes inverse matrix. So inverse matrix times alpha. Okay, and then alpha is a constant, so you can put inside of this term. So you can see what's the result. So we just simplify this equation like this way. Alpha here take inside, and alpha for this the term here, you can see if for this term, do I have anything missed? Yeah, this is inverse, right? So alpha taking 2 is inverse. So alpha, this is inverse, so it's 1 over alpha. So times out is cancelled, become constant 1, and this one become inverse of the alpha because there's a inverse here. Be careful. Yeah, here, inverse there. So the result is our estimate through Lagrange multiplier and through calculus optimization approach. We can estimate our new image f like this one. Your observed image, your degraded function h, and your try to optimize objective matrix. So it depends how you choose the Q, what you try to optimize and constrain to your degraded image there with this parameter. Okay, so we try to choose, you can use this one to satisfy this question, sorry. Yes, okay, so I change your little screen out, let's go back to the first page. Okay, so we can see after this optimization approach, we have the solution like this. This is our final solution here. Final solution, optimization solution. This is equation we will use quite often. Okay, f hat equal to this one. So it depends how you choose gamma, how you choose the Q matrix. Okay, so let's see. We first will face this pseudo inverse filter and also use this optimization result here. So what is the pseudo inverse? So the pseudo inverse filter try to avoid the pitfall of the applying the inverse filter in the presence of noise. So we know if there's a 0 there, if you inverse, okay, they'll become enlarged, the noise. So see, that's a result previous we approach from Lagrange multiplier approach here. And with this Q equal to I, there's a pseudo inverse filter. and it is kind of like this equation because Q is the identity matrix. So identity matrix take the transpose and then times itself is still identity matrix. So Q, if you assume it is identity, it's a pseudo inverse filter there. So what's the result for optimization for the pseudo inverse filter? The F hat become Ri gamma I, and plus this transpose of your degradation function. Sorry, there should be G there, miss a G vector there, the observed image there. And you can try to use this in Fourier transform. It's much easier. Okay, because it's a lot of application, multiplication operation, matrix operation. But if you put in a Fourier transform, it's directed, give you the result. So later on, we'll give you example how to do this one. Okay, so if you process this in the Fourier domain, much easier. Like this one, R is now this one, take the transform into the Fourier transform domain. So F become FUV, G become GUV, and this previous item will become RUV. So RUV inverse transform actually is just like this result. Actually, it's complex matrix equal to transpose matrix in a Fourier transform domain. So H star is equal to HT. So it's complex complex conjugate, and this is transpose. If you see this in your textbook, so you can see the HT transform is a conjugate in Fourier domain, and this is in denominator, and it's a R transform, and the HT times H is become H squared. Okay, so you can see our result just like this. So you take your degradation function, take the Fourier transform as denominator, numerator divided by H squared plus gamma, because you assume your Q matrix is identity matrix. We design a pseudo inverse filter. So simply it's become like this. So then sure you can modify this one like this one. Take the 1 divided by HUV as your cofactor. You don't have to do that as well. But please look at this one. This is depend on the gamma. So the gamma here is our previous lambda. Our Lagrange multiplier, I think it's become 1 divided by Lagrange multiplier coefficient. However, if you choose this parameter, gamma is constant there, different from our previous inverse filter. Because our inverse filter is just like you do this one. You just take a GUV divided by HUV, right? This is a traditional inverse filter, but we have seen that the result is very poor, because you enlarge a lot of raw message there, especially the noise, you enlarge it. So we do some pseudo inverse, so it becomes some parameter occur here, the gamma here. So the gamma equal to 0. If you take gamma it back to the inverse filter again, because you see it's gamma is 0, is will be cancelled out, and only this left. It's an inverse filter again, right? Your RUV become 1 divided by HUV, so it's inverse filter again. So your gamma is important to protect some huge error there. So this is you have to choose this gamma. If gamma equal greater than 0, the denominator of the RUV is strictly positive, and pseudo inverse is well defined. So the pseudo inverse filter also come from the optimal solution, but your Q is used very simple design. It's a identity matrix there. So it's a pseudo inverse. So let's see what's the result for the pseudo inverse filter, and compare to previous maybe inverse filter. Okay, so we go through a lot from our optimization problem use Lagrange multiplier, and we see what's the result here. So the pseudo inverse filter. Okay, remember pseudo inverse is like this one. Okay, you have this degradation model, and you have this gamma constant there. So for example, like we use this one. H is the degradation model, is Burr function, right? It's, you use the uniform matrix, it's a block matrix, it's a Burr function. So F is the original image, G is the bird function. So G equal to H combined with F and plus some eta. Eta is the zero mean Gaussian noise with the variance 0.00, a very small one, very small Gaussian noise. Okay, so we know this one. Actually, we change it to a matrix format. It becomes G equal to HF plus eta. Okay, if you use a matrix vector form there, so it's the same. Anyway, this is the image you observe. When you move this Waxburg filter, combine with this Waxburg filter, and then add the Gaussian noise with small variance. And we have a mean square error is 0.01. So mean square error is compared to your original one, and then take the error, take the square, and then take the mean. So the lower is better, okay? But now we have a 0.01. So how can we use our pseudo inverse filter to solve this problem with different lambda? Okay, our previous we say lambda is different gamma, different coefficient here. So if you choose this 0, it go back to inverse. We will see what's the result. So please see this different. If you take the gamma equal to 0 here, so actually it's an inverse filter. Okay, you just give up this your Lagrange multiplier coefficient, and then take it to 0, and the mean square error becomes huge, 2.7. And then we can try to tune this parameter. So how you tune it? You can use different trial. So maybe use 0.01, maybe use 0.075, 0.5, and you can go back to compare what's the result. But it's always better than your inverse filter. Okay, so you can see the mean square error used 0.001 is not as good as your imagination. So you are going to increase different gamma coefficient here. And if you increase too much, actually it doesn't help. Sometimes, see, if you do this one to here, and then when you keep increasing, the gamma is become mean square error become lower because there is some balance between noise removal and bird function removal. So both you have to do some trial for different gamma for your pseudo inverse filter. Is that okay? So it's the traditional way. So you object this Q, F, minimize this one, and then constraint subject to this condition. Okay, and so we use a pseudo inverse. We assign Q equal to I. We call it pseudo inverse filter design, but we get this result. But we use different gamma here, and we have different improvement from 0.01 to 0 down to 0.0076. Okay, mean square error become smaller, it's better. Okay. Okay, so let's look at winner filter. Okay, we have another design called a minima mean square error filter. Also, you can call it a winner filter. It's back up to I think more than 30 years ago, 40 years ago to do it one. How we do that one? Actually, is focus on your signal noise ratio. So it's not use a constant gamma layer. It depends on what? Depends on your signal noise ratio layer. Okay, signal to noise. So how you compare your signal to noise? Actually, they can do some correlation matrix here. So F is your original image, and take the expectation of F vector times F is a image vector already, right? So if you know, we transform this two-dimensional to matrix vector format. We pipe up all this column low vector translate into a column vector. So it's very long column vector, and then times this on F transpose. It's from two dimension. And what is this? Actually, it's a power spectrum of your image. So, and if you take the expectation of this one, expectation of this your image low vector times transpose low vector become column vector times row vector. It's become a two-dimensional image. And you take an expectation of this one, we call it power spectrum. Power spectrum of your image. Okay, if you take a Fourier transform, it becomes power spectrum. Take Fourier transform of this image times image together is square of the image. Okay, and how about noise? Again, the noise is also eta vector. So if you take the correlation operation of this noise vector, we say it's eta times eta transpose. If you take the expectation value, we define this as the Rn, correlation of the noise. If you take the Fourier transform of this noise, we call it noise spectrum, power spectrum of the noise. And for our assumption is your every location of your noise are different. So maybe the winner suggests every different Fourier transform point use are different. So they depend on your signal to noise ratio. So if you take the Fourier transform of the RF divided by Fourier transform of Rn, okay, this is the autocorrelation of your image, autocorrelation of the noise, and then take a Fourier transform. And then if you take a log, and then it's called signal to noise ratio, SNR. Okay, so now if we change, okay, remember this equation again. This is our optimization solution there with a different Q, different optimized condition, and we constrain to your noise model. And Q is you are going to design. So Q transpose Q is you try to minimize your issue. And then if we change this one to what? Q transpose change to like this one. Okay, it's inverse of your signal noise ratio because it's in a denominator. So we take the inverse. Okay, this is SNR, signal divided by noise. But you see, RF inverse times Rn. So it's become inverse of your signal noise ratio. Okay, so this is the winner proposed is optimization approach. So remember that Rn, RF is the power spectrum of this your image and your noise. Okay, so see, we just define this one. Define this QT transpose T like this one, inverse of your signal noise ratio. What's the result? So like this one. So it is the winner filter. Okay, we will try to minimize the noise to signal noise ratio. Okay, originally signal to noise. Now it's a noise to signal because it's upside down. So it can be right again like this one. So previous we have this one exactly the same. Okay, the RUV is exactly the same like this one. And okay, so similar. Okay, just do some simplification. So never mind, you just take a quick look. So actually exactly the same format, just QT transpose times Q, change to noise to signal ratio. Okay, inverse. And what's the result? If this one is equal to 1, gamma equal to 1, it's defined as a winner filter. Okay, you just replace all this noise to signal ratio layer, and it's called winner filter, gamma equal to 1. Again, if gamma equal to 0, if the coefficient of gamma equal to 0 again, so this term disappear, and it's cancelled out. It becomes 1 divided by UV again. So it's become inverse filter again. So it's now good for this gamma equal to 0. And the gamma between 0 and 1, so we call it parametric winner filter. Gamma, the coefficient belong to 0 to 1. Okay, so in this range, it's a parametric winner filter. It's all winner filter because you take the noise to signal ratio as your QT times Q. And so it's a winner filter design. So actually, we just see from the result here. So we don't have to run this again. If your noise to signal noise ratio is equal to, if you write this easier way, it's equal to rho, your SNR, okay? Signal SF spectrum divided by SN spectrum, we call it signal noise ratio, right? We use a low to represent. And we have a gamma here, and it's an inverse noise to signal. So we take a denominator. So actually your RUV is just like this one. So we just mentioned gamma equal to 1 is a Wiener filter. Gamma equal to 0, it becomes inverse filter. Gamma between 0 and 1, it becomes parametric Wiener filter. So it depends on how you choose this one. Okay. This is the example for this Wiener filter. Okay. All based on this optimization problem, and we have different design for this Q. Okay, your Q. Remember, our objective function is a Q, QF. Okay, try to minimize this one, and subject to our G equal to HF plus N eta, and yeah, so equal to 0. Try to subject to this condition, and if in this example we use what? Use this degradation filter is Butterworth, right? So if you look at this format, it's a Butterworth low-pass filter. Perform the Butterworth-Lopez filter to degrade your original image. It's smoother. Okay, becomes smooth. And we use some noise there. Again, here we try to use inner filter because there's some noise, additive or noise there. Otherwise, you just use inverse filter. Very good result. And we don't know what's the active noise there. Here, if we assume there's some noise, and the noise signal noise ratio give you some certain result there. Okay, so it depends. So the low equal to this one, the signal noise ratio. We have 3 different additive noise to change its signal noise ratio. Remember, low equal to SF divided by S eta. Okay, signal to noise ratio, the power spectrum. So yeah, they are different signal noise ratio for 3 conditions. When it's higher, which means your noise is not so much because signal to noise is a larger dB there, so which means the noise is small. If the low is smaller, which means your signal to noise ratio is a very small, which means you have a large additive noise. However, okay, if we use a small gamma here, okay, remember the equation here becomes gamma divided by signal noise ratio here. So if you use a small one, it means you try to remove your noise, not much. But unfortunately, no matter how your signal noise ratio condition, it's all bad because gamma is small. However, if you use a Wiener filter, you can see the result much better. Okay, than that one. So which means if you use very small gamma, which means like a inverse filter as well. So the result is not good. Okay, so that's a Wiener filter. So you have to adjust. Unfortunately, you have to adjust it by yourself, or by your experience, by your condition of your noise, because you don't know what's the real result, what's the real condition in your degraded image. You just estimate. Even the H filter, you don't know what is the motion blur, what is the linear motion, or what kind of low pass filter to degrade your image. We taught you 3 ways to estimate H, right? So you have to find H, and then you have to find gamma. Use the Wiener filter to improve your image. So compare it. What's the improvement? Okay, so it's a parametric filter again. See here, we can see parametric filter, which means we have use more different gamma there. Try to from small one to large one here. So the small value here is just tell you the result. The small gamma, remember we use gamma divided by rho in our parameter here. Okay. Here is your selection of your parametric Wiener filter. So if you use small value, actually result in better blur removal, but poor noise filtering. That's what we mentioned. If this is a very small amount layer, your noise removal is very bad. So you enlarge your noise content. But if you use large gamma, and it's not good for your deeper function, but good for noise removal. So it's just take away the noise as much as possible. But unfortunately, your blur function removal perform not good. So you can see the gamma is big. Okay. So it's changed like this condition there. If your gamma small, the noise content will be magnified a lot. But the gamma is large, no noise, but blur function is poor. Okay, so both conditions you have to consider because our image is deferred by your deferred function, degradation function, and also we have some active noise. So we have two challenge to solve this issue. So either way, so window filter tell you if you select different gamma, you have different target to solve. Maybe you want to remove noise as much as possible, or you want to solve the deferred function as much as possible. So you have to do some different trial and then see what the result is satisfy your purpose. Okay, so I think this one is also the same. Okay, it's try to optimize this one. This issue, this example, they try to optimize based on the smoothness of the edge. Okay, so they change the Q equal to Laplacian operator. So try to minimize the smoothness of your edge. So remember our equation is h divided by HUV square plus gamma sum QT trans Q, whatever. Okay, so here is try to use a Laplacian. Okay, let's check. Try to smooth the Laplacian operator there. So what's the? Maybe we. Let me see. This one is winner filter, result inverse filter. Oh, sorry. This is not yet. Okay, this is compare previous approach. Remember, we have give some inverse filter, right? Immediately use inverse, but the result is like this one. So if you have active noise, you have deferred function, but use inverse filter immediately, the result very bad. But remember, we have some radial limited inverse filter. We say this is the inverse filter, H inverse, and then we use only partial of it. And this one, don't do division, don't inverse. Only care the central part, different radial. Okay, go back to check the example previously. And you can see it can save some high frequency part without use the inverse filter, because our inverse filter are always very small value in outsider of the filter. So when you have small value and it's in the denominator, one divided by the denominator, it becomes enlarged the noise. This is the way, the result. You amplify the high frequency noise there. However, if you use limitation, if your filter outside of this small radius, small circle, don't care, don't divide it, don't do the process, and it's look like pretty good. But compared with this winner filter, actually similar, and the I don't know if you can tell the difference. Look like winner filter have sharp edge there, better result. Okay, if you look at this center building there, for the winner filter they provide, because they consider both blur function and the additive noise together simultaneously. So that's the way to tell you. If you use a lazy way to do it, okay, it's also work. Just careful, your radius you have to choose. In previous example, we have a small radius, 50, 75, or 80 something. When you have a large radius, it's become this result as well, because like inverse filter. But if you choose some right radius of your inverse filter, it's okay. You can recover it in certain good result. But if you use winner filter, it's better. Sharper edge will be remained, and also the active noise will be removed. So we will see later a lot of different examples. You combine different winner filter design, and also we can set up the Q transfer Q in different way. Okay, how you maximize, how you minimize the smoothness of your edge, and then for example, we just mentioned the pseudo inverse. You take Q equal to I, and you have some winner filter take the inverse of the signal to noise ratio. So it's the key you to do this one, and also you have to select right gamma to satisfy your final result. So let's take 10 minutes rest, and then we will see some different performance of this optimization restoration issue. Okay, I'll take 10 minutes rest.
我最后是
暂停一下，暂停。好，
最后就是设计成这样，就只是就是请他们实做这个方学，然后 K 我直接请他们用一个常数，然后这个常数就用 SNR。哦，用
SNR 对，好，
好。就是我就设计了一些方选让他们实做，然后
不同的那个不是方选吗？
就是我一开始先让他们创一个。
motion blur
对 motion blur 的 kernel，然后再就只是请他们用在 business domain 里面直接去 blur 它。
好。
对，然后最后先用 inverse 直接 inverse 跟 winner， 然后去比较两个。
OK， 很好，这样就可以。K 档就是不一样的。
好。
要算它的 MSE 呢，才能够知道谁比较好。
好 ，OK。
呀，是。这个是。礼拜讲半天，这个式子，你说这个式子等于这个怎么来的？我们不是就是原来的 minimize QF 吗？你的问题always是 minimize， 然后 subject to 你的条件嘛，到你的条件就是 G 等于 HF 加上或是 G 减去 HF 等于它。QF 就是我们现在在讲啊，就是你的 design， 你可以去 minimize 你的any issue 啊，现在刚才我在讲，你 Q 可以是 minimize 你的 smoothness 的音乐，所以我去解回来以后，音乐还是要保持它边缘不要太复杂太差，不见了，因为被处理过会不见了。好，所以这 Q 可以很多种选择。winner filter 就是 Q 选择是导数 SNR 的导数，这是我们解出来的 QTQ 所以这个是基本的问题，所有的问题都会是我要去 minimize 什么，像这个就是我要去 minimize 我的 purpose， 你可以 minimize 说我要误差最小，现在就是大部分都是说我解回来之后，我希望边界保持最完整 ，smooth， 我的 edge 保持最好。都有一个不同的条件等一下我们在讲 Q 我会设计成它的边界，比如说它是5，这是什么？还记得这个？这个吗？打发线，对啊，打发线，从它 edge， 那 edge 以后 minimize 就是它的 edge 里面最 smooth， 就这样的看法。所以你也可以不要做什么，就是这个是解这个可以解出来它的条件当然就是这个。我们就刚才解半天都在讲，它的结果就是这个，因为它是从光学得到最佳解，就这样子。这就是最佳解，就是最佳解，这个以上就是最佳解。你怎么找到？你从这个条件是什么？它像我们刚才不是举例嘛？我的 minimum 或是 maximum 的 XYZ 的，我要没有的 B 啊，这是一个条件，你想要达到的目标。对。配上这个条件的限制，
那个条件就是那个，
因为对 image 的时候，它就是这个情况啊，这个条件就是它被它污染，被它干扰，所以它有这个条件在限制它，你要背上这个条件限制去找到最好的切割的解。
然后是用那个拉格朗
来找，对， 就 background 就把这两个组合起来，然后再有微分，就这么简单的概念而已。就是
看你要 optimize。
对，你要把这个 subject function 放进来，然后你原来 optimize 的这个函数，就我们刚才不是就为什么要讲这个？因为我知道你们看也看不懂啊，课本就直接这样给你。我上课本嘛，完全课就给你solution，说你应该知道这个方程的结果，答案就是这个。那现在可以懂吗？现在懂我们在做什么吗？你的 objective function 有了，然后 subject to 这个东西也是一个最佳化的问题。你要条件呢，这可能条件好几个嘞，不会只有错。
因为我们一开始我们就是在这边讨论，然后我们
没有，我们的 restoration always 是这样的 ，always 就是说你要 minimize 什么，你要去讲，你开始就一定会讲，我 minimize。对，这是你现实的嘛？那你今天要解决问题的是，所以你看，我们刚才看到我在不同的选择，我得到的结果还是会不一样的，就是我可能会解决不同的选择问题啊，你要看到什么？你要看到说我们原来什么，然后等下会举个例子，你什么都看不到，你要看到两个人，你不知道啊，但是你会出来。你要想看那影像，像以前是用手的签，然后说这是什么，大家看不出来，看不出来。可是你看到的轨迹是有一个水模糊，那个影子是这样子，那个影就是那个阴影是这样水，所以看一个是水平的 motion， 它是用水平的 motion H 去 estimate。它我们讲我们可以用3种方法，一个用睛看就看得出来，一个是拿你的 point source 到你的这个设备才知道说，它会。再来就是用你的常识，你从那里来，外太空的，你可以去马上 H 大概知道，可以 estimate。那但是你不知道它是什么，那你如果知道这个东西，你直接就死了。你可以把说这个影响出来就更惨，什么都看不到。但是如果用 Windows 对，你不知道，因为它有 noise，noise 的话你用 inverse 就一定最惨，因为你 noise 会会，
所以才要调那个伽马。
对，伽马。所以我跟你讲，你也可以不要用最偷懒，就是我 inverse creator 然后缩小，这是一个方法。说真的，这也是一个很快的方法。用小小的 inverse creator 范围内这一条，高频的不要去弄，因为高频你的就很低，那你就用 inverse creator， 你的高频很低，你会放大。它那种是 everywhere 啦，那我们那里其实什么假设都是高线嘛，高线那里这边有没有？所有频率都有。你大概除以很小的值，这些一除的话，这可能就是降低下来，是最放大的，所以你什么都看不到，可能更惨。那这东西其实用嘴巴讲，其实要那你说我都不知道原来影像，没办法。但是我们给你的题目是我有原始影像，所以你可以告诉我 MSE 是多少，你用你的数据以后，你得到 mean square error 是多少，你有没有叠加？你可以出来。好不好？这没办法，这个 restoration 就是这样子，什么都没有就拿到一个结果。但如果有 system 那很好，因为 system 是可以让你找到最好的。那 H 去 inverse， 就是得到的这个除以 H， 它照样是最好的。对不对？你可以对它一开始讲，所有人一开始讲这个，就没有 noise， 真的很不幸的，你真的加 noise 画出来。就要这个，好不好？那个只是一个 object function， 你要告诉我要 minimize， 等一下我们就是会举个例子，我要什么H 出来以后，它结果 H 我要发现其实是不一样，好不好？
老师刚才是用这个还是？
好像用那个，对，它是不一样。Okay. Yeah. So let's recall your memory. Okay. In an example of this figure 5.27, it's Butterworth brewing. Okay, but we use inverse filter with different cutoff outside. So this is the 40 radius of 40 pixel, radius of 70, and the radius of 85. So you can see we maybe compare with this 40, and if you use a full filter, Butterworth full filter, because you know it's a degradation model. Even I tell you the degradation model is satellite deferred function there. You just take the inverse and you get this result. Okay, and even there's yeah. So I think it's just try to compare. Okay, definitely you can try always use the inverse filter, but with different radius. Maybe you can see something there. Okay, your degraded image. If you just know your condition is satellite deferred function, and take the inverse filter, immediately you get this result. You see nothing. Okay, you see nothing there, and you use different trial, you can get this a better result. Now we are comparing with this inverse filter and with the Wiener filter. Okay, with different gamma there. Okay, so this is just tell you. Okay, if you take this one, and if you use Wiener filter, you get better result. Actually, if you want to perform compare, if this is better, you have to calculate MSE, okay, mean square error. So our homework, next homework, the less homework for you is try to go through this restoration problem, and we'll give you original image. I'll give you yeah, later we will see. Okay, don't worry, you can do it easily, but go through it, you will know how to do restoration optimization problem, and just give some result to compare. Which one is better? Which gamma is better? Which k? Which coefficient here is better? Okay. Here is another example. Okay, in text. This is corrupted. The image A is the image corrupted by motion blur. Okay, and additive noise. So to tell the truth, if you see this image at hand, do you know what's the content there? Can you tell me what's the content of this image? Unless you read your textbook every day and then take the cover page. Okay, actually this is this textbook cover page. Okay, okay. So if I gave you this one, it's just bird and additive noise there. You don't know what to do. So maybe you try to use inverse filter. Okay, so can you tell me what kind of inverse filter you're going to try? You have to make a guess. What is the edge? If you look at this image, as you can see, a lot of this blur direction. So actually, it's kind of motion blur and in a negative 45 degree moving. Okay, so your edge can design like this one. Right? It's motion blur. Okay. So in our homework, I don't. You give the horizontal. Okay. So yeah, I don't have. Yeah, you will see how you deblur your image, and you see the result. If you look at the result, try to make a guess. Okay, make a guess. What kind of deblur function you are facing? This one is the second B is the result of inverse filter. Okay, again. So you say, oh, I have this one, and I know it's a deblur function in this direction, and I have the edge. You are right, edge is like this one, 45 degrees. And then you apply inverse filter, and then get this result. You see even worse result, and you can explain what's the reason, because of the noise. So maybe you try to use your inverse filter, and then small, I don't know, you can try a small radius to change. Maybe you can see something there. So the C is the result of inner filter. Okay, so let's just give you one more protection, because we know we have two degraded resources. One is a blur function, the other one is additive noise. So we cannot ignore is there any additive noise. So if you use additive inner filter with different gamma selection, and maybe you will get this result. And compared to our original one, this one is better, right? And you can see digital. like image, like processing. Okay, yeah. But anyway, it's not good as well. So how can we do? D to F, the same sequence, but with noise variance, one order magnitude less. And let me see. Okay, the Gaussian degradation Gaussian noise. The condition is the mean of the Gaussian mean of noise. Gaussian noise is 0, and sigma of the Gaussian noise is 650. Okay, in this example. Okay, motion blur and Gaussian active Gaussian noise. But if we just lower down the variance of the Gaussian with one order, okay, so D to F same sequence, but with noise variance one order making it less, so maybe it's 65 for this one. Okay, maybe because you know what it is, so you can see, oh, it's a digital image textbook. But if you use an inverse filter again, sorry, nothing occur. Even if one order magnitude noise decreased, still get nothing. But here is the result you have to compare. So even less noise, you can get a better result there. So how about this one? The third row, same sequence, but noise variance reduced by 5 order, still noise there, active noise there. So this is the same motion blur, but the noise 5 order less. Okay, so it's only small amount of noise, but now it is almost no noise. Okay, very, very small. But if you use some inverse filter, good. You can see this one, but there's still somewhat the motion issue there. But if you use some Gaussian, winner filter, you get this result. It's less active noise. That's great. The motion blur can be solved in very good condition. So it's a comeback like this one. So from this one to this one. So at your hand, maybe you see the image like this one. You can tell nothing, right? You don't know what's the condition of your noise. What's the condition of motion blur? So you have to try. You have to try. Unless you know all the condition in hand, you have the system. And if you don't know the H, we can say we have 3 different approaches, right? It's a knowledge-based, it's an experiment. You have a system, give the point source, and you get a result. It's your H, the blur function. Or use some specific expert knowledge, is a satellite image, what kind of image, or look at this image is kind of motion blur, and you can make a guess. Okay, what's this? This is another approach for because we use our system like this one, right? Like H star H and square plus gamma divided by rho to your system. Sorry, square and to your system G UV, right? Whatever. Okay. So it's a winner filter, and we always try to use a very simple approach. Here we just put a constant winner filter, put a constant K here. So K you can adjust 0.001, 0.005, a different constant here to solve your degraded image. Okay, with some additive noise, and this is the result. Result of constraint this square winner filter. Compare ABC with the winner filtering result, respectively. Okay. And what's this? What's this one? Let's try to compare this one. Actually, these three image. Okay, with different noise. I think so. Yeah, it should be. Okay, you can do the text for detail. Okay, so you have 3 different winner filter and with different noise label. Okay, and now we can have other trial. Not only use a constant K here. So you can try to modify your objective function. For example, like this one is try to minimize CF square. Okay, subject to the same condition. Okay, so the C here is try to smoothness your result. Okay, so which means we want to look at this optimize restoration on the measure of smoothness. Okay, smoothness of your image. You can do different choice on this QF there. Okay, so if we want to see the smoothness of edge, what do you do? What do you do before? How you get the edge smoothness? Actually, they try to give you some example called Laplacian operator. You take the second derivative on your edge, right? Laplacian. Remember this operator there, right? So it's a second derivative. If you look at the image processing in chapter 3, I think. Yeah, so you have this image, this filter like this one. The Q can change to this one. So here, they define like this one, so F hat, you can equal to what? H star here and H square, HUV square. Gamma also the Lagrange multiplier, and the Q become preview V square. Original for the Wiener filter, we take the inverse of a SNR, signal to noise ratio, upside down, and now we are going to change this one to this one filter. PUV. P is a Laplacian Fourier transform. Okay, so you can do different minimize objective function. Okay, so here just change this one, and you can compare for different level of noise degradation. Active noise, different level. This is the original 650, and this is 65, and this 5 order, I don't know, they didn't mention, maybe only 0 point something. Okay, sigma variation only point something, very small. And for compare result, you have different purpose. So here is you didn't describe, you are going to smoothness your edge there, but here you can see this one compared to this one. So you have to put these two together. This one and this one. Is this clear? More clear than the other one? Traditional Wiener filter just gave a constant there. So I think it's a lot of different way to evaluate your result, which way you like. So you can see the image here, even the character very clear. But for this one here is yeah, it's also clear, but it's smooth. Okay, so different purpose. Okay, different assumption. So the textbook also give us some different trial for different purpose. You can reducing effect of the noise in different trial. Okay, so if we want to measure the smoothness of your image, you can try use different approach of your optimization restoration. And here is the way. What's this one? This is try to iteratively determine constraint this square. Okay, so we just mentioned in previous example, we say, you just go try and error, use different gamma, 0.01, 0.02. Actually, you are going to do it in your homework. Okay, maybe you can try to do some advanced level, try to compute it by iteration. Okay, so here is just give you some specify some spatial value. Okay, so if you you just define your iteration by gamma vector is a G minus HF. What's that? It's supposed to be eta, right? It's supposed to be your noise, right? So a textbook can tell you if we define a new function, gamma of this one equal to this one, okay, it's more computation there. Okay, if you are doing some detailed automatic approach, maybe you can see this function, define this function. It is kind of monotonic increasing function. Monotonic increasing function of R. If not, you cannot do this. Okay, increasing function of this one. Okay, so you can do some program running, try to do some iterative iterative operation. So you have 3 steps to do. Specify the initial value. So you still have to make a guess. Okay, initial value of this one, and then second, compute of this one. We just define. This is vector like this one, transpose vector, and we are going to have this one can be multiplied by what? Define this vector is our original eta plus or minus some function, some value there. So this is the way we want to adjust. Maybe the better is the worse. So we don't know what's the value we are going to assume is the best one. So we assume there should be something, maybe add up some value alpha layer or minus alpha layer because we don't know the good result. You see our previous example, we say 0.01, 0.05, 0.7, 0.1, it can be worse. So it's sometimes you don't know what's the exact value. So the third one is try to stop if we find it satisfies the result already satisfied. So it's adjust it, and then until it's equal to this one, satisfied. Otherwise, so you have to see, we assume it's a monotonic increasing. So it's increasing, we are going to increase your gamma. Okay, if we found gamma vector, it's smaller than this one because it's not achieved this one yet. So you are going to increase it because we assume it's a monotonic. So when it becomes less than, it's minus something, but it's still not approach that the result. So you are going to increase it or decrease your gamma if cannot write. If this one larger than this one. Okay, so the post condition. So you are going to do it iteratively. Try to find some suitable gamma number for your result. So it's just give you some idea. Okay, you can maybe try to write up a automatic program to do it. So this is the way the compare. So this one is use gamma equal to -5, and then you just automatically adjust, and then they will tell you this equal to this one is the good one, and alpha is 0.25. So you get this good result. But if you just do it intuitively by your guess, it will get this one. So to tell the truth, I cannot tell much difference from these two. It's automatic, but some variation you have to compare this through MSE. Okay, otherwise you will get this one. They say this one is the worst, but to me, I think I didn't tell the big difference between these two. The result attend the wrong noise parameter. So I don't know what is the right one. I just give a try, 0 point something, and then maybe some look. Can you tell the differences from your textbook? Please take a look. Maybe I think this one is clear edge than this one, but to tell the truth, not so clear. Okay, so anyway, they just give you some suggestion. Maybe you can do it automatically to find this gamma. Okay, yeah, I think this is the chapter 5 restoration issue we are going to introduce, and now we give you some the real example, and you are going to do the homework. So. So no worry about this one. We'll give you the example how you do it. And this is the classical restoration motion deployed by window filter. So at least you have to know what's the window filter. So do it by hand. And if your MATLAB is not familiar, so I provide you the source code there. And so we use a horizontal motion blur. The D is equal to 40. So what's that mean? We just try to use some pixel, 40 pixels deblur. Okay, H is the 0, 2D by 2D, so it's the size of the H, 2D plus 1, 2D plus 1. So it's O0 original. And we try to define this D plus 1 to 2D plus 1. So D plus 1, so in the center, and 1 to 2D plus. So I have a horizontal line with a 1, right? Okay, just assign. And the value of this one is 1 divided by 2D. Okay, not 1, 1, 1, 1. It's a constant of this value. So add up is 1, right? It's just very easy for this 3 define our horizontal blur, motion blur function. Okay, so it's like this one, 1 over 2D, 1 over 2D in the center, 1 over 2D, 1 over 2D, and O0 other where, because there's 2D plus 1, 2D plus 1. Is it okay? I just give you a motion blur function. Okay, blur image, how can we do that? Just give you a linear and FE. So FE is extended because we are going to do convolution, right? So convolution is F convolve H. So if this is M by N O by Q, so it's the result should be the image is M plus O minus 1 by N plus Q minus 1. So it's a previous, it's the convolution size will be enlarged. So here we use some FE. F is original image, right? And FE is called extended. After your convolution, your image size will be extended. Okay, you have to have this conception in your mind. So you can see M is your original size. Mn is the size of your F. M is the width. N is the height. So plus 2D plus 1 minus 1. So 1 cancel out. So this is the final size after convolution, right? Right? Your H is 2D plus 1, 2D plus 1. So your F is the M plus N. So this one plus 1 minus 1. This one plus 1 minus 1. So you can see that's the extended image. And we put the first one F. So what's the that mean? So you put your linear here. And this is the extended 0. Okay? This just let you know our image should be the right size to process because you are going to transform into Fourier transform. But dimension very important. Otherwise, you cannot do multiplication and division. You are going to divide 1 by 1 pixel, so all the dimensions should be the same. Okay, so H, what's the H? Again, H, you are going to change to the same. Your deblur function change to the same size. So we use HE. Originally is H. HE is extended. HE, so it's the same. Your image extended like this one. Okay, your deblur and this O0. So it's just your extended 0 padding on your original image and your blur function image. Okay, so now let's do some active noise. So random noise, and then with the size. So we have a noise. We have extended HE. We have an original extended image. Going to do transfer to Fourier domain. So if you have a capital F here, which means after Fourier transformation. So FFT shift, FFT2 is very easy. FFT2 is very easy. It's just 2-dimensional FFT. And then why we do FFT shift? Because you want the low frequency component in the center of your output, right? You can see it clearly. So our all Fourier transform have performed FFT shift first. Remember that, okay? If you look at your frequency component, all the center in your image, frequency domain, low frequency part in the center. High is at the corner. If you don't do this one, your low frequency will be at the 4 corner. so it's not obvious to observe. So G is, if you want to go back to look at it, what's the G? G is the F convolve H. So can you get a G if they only have a noise? So you can see Fourier transform of extended image, Fourier transform of the Bird function, and then remember dot multiply. Okay, there are two matrices in Fourier transform, okay, with the same size, and you are going to multiply together. Or in Fourier domain, it's not a matrix operation. Okay, very important. It's point to point to operate. If you miss this node, you'll have big trouble because your matrix operation will be this column, this row times this column 1 by 1, and then become the first output here, right? And the second row, first column, second row, first column will become this one. Okay, and the first row, second column will be here, right? So it's a basic matrix operation. If you in MATLAB use this multiplication symbol. But if you want this point, multiply this point as this output, you have to dot multiply. Okay, so very important. Don't miss this dot. Don't miss this dot here. And in frequency domain, this image times this image in Fourier frequency domain, there's some blur result. And I take the IFF2, go back to spatial domain. It's our blurred image. Okay, so the image was blurred by horizontal motion blurred. And for this one and this one, additive noise. So we have GN. GN is the observed image is active noise. So different. G is no active noise. GN is with active noise. Random noise there. So Fourier transform of G is FFT2 of G. Fourier transform of G with the active noise is FFT2 of GN. So we have all this function there. Okay. So remember, if we look at this symbol, we know what it represented for. Okay, with a capital F is in frequency domain. With N there, with active noise. Okay, F is original image, with E is extended image, and H is the Bird function, with E is extended. And let's see, if I give you the image here, okay, Lena, and we want to see the Fourier frequency spectrum of this image. How do? You just take the image, right? The image without noise, without a transformation, without blur, and then take an absolute value, and because you take log amplitude, because you have large, the more 1,000 and 10,000 too big, so we are taking log magnitude. And to add 1 is try to avoid the 0. Log of 0 will get an error, so we get 1 there, constant label there. So you can see the frequency amplitude there. And there's a maxima, and we try to see the result like this one. So this is the Lena image in frequency domain, their energy distribution. Okay, also this low frequency part with a larger component energy spectrum here. So now let's see image G. Okay, so if you want to see, we have a motion blur in horizontal result, just like this one. So if you look at this one at hand, do you know it's a Lena? Unless you love this lady very well with head. Otherwise, if I give you this image, how can you see it's a Lena, the beautiful Lena? No. So it's a motion blur, series blur there. And this is the corresponding magnitude spectrum. Okay? So this is the Lena image with motion blur, horizontal motion blur, with active noise, because it's GN, right? GN here, so you know it's with active noise. Can you tell the difference between this one and this one? Not at all. You never tell a lie. You cannot tell the differences there. Okay, so this is the noise spectrum of the Lena image, bird Lena image with active noise, Gaussian noise there. So now we are going to do restoration trial. So when you get this one image, you see, okay, it's Lena. Okay, I tell you it's Lena. Motion blur. Okay, it's horizontal, and you know I'm going to try use inverse filter. So here is a K equal to 0. So remember our frequency transform HUV and H square, right? H square plus K here, winner filter, right? So in Fourier domain, it's very straightforward. Okay, as long as you define the K here. So winner filter, we say is a parametric winner filter. If you put 1, it's winner. If you adjust the K, it becomes parametric winner filter. So F hat is what? So you just do this one, apply to your image, okay? Your image GUV, and then take inverse Fourier transform. That's the result. So how can you write this one? We will demonstrate all these results, okay, and show you how to use Lagrange multiplier, get this function, and you just simply see FHE, Fourier transform of extended this one, H, okay, and then take square. Sorry, that should be a square there. Okay, so here's square, here's also square, and divided, also dot divided. Remember, okay, dot operation is element-wise operation. Divided by what? HHE square. Every element take the square plus K there, and then times what? Fourier transform of G. Fourier transform of G divided by H of E. Okay, so if you type square here, there should be some H here. I forgot the equation. Please go back to check. So if you take square here, there should be divided something there. Okay, so see if K equal to 0, here, this condition, K equal to 0. So there's nothing add up after this one. The denominator, there's no K equal to 0. So even the K there doesn't matter, it becomes inverse filter. And you show this result of inverse filter like this. So this original, like this one, and then you get this result. Like your inverse filter, nothing left. Okay, but now we are going to do some trial. So if we have time, at this try maybe 3 different K. Okay, it's okay, 3 different K. And this small K there, and see, exactly the same equation. But I add some small K there, winner filter, parametric winner filter, and then the result like this one, immediately. Okay, so we say you are going to increase because it's still a lot of Burr function exists. So we are going to change a little bit. K equal to 0.005. It's better, right? So you have to try. And then K equal to 0.001. So 1000530 002001. It becomes like this one. Okay, and then try again. 0.1. Which one is better? Which means it's over, right? So you have to make a balance between your Burr function and your active noise. Because I don't know the active noise, the label of the active noise. I don't know the Burr function, the condition of that one. So you have to justify which one is better there. Okay, and if you take a 0.5, become like this. So the conclusion is your parametric inner filter, the K is not as bigger as better. Okay, if it's too big, like this one, this is K equal to 1. Okay, you get this result, just like an inverse filter. You see nothing there. Okay, so you have to do some choice in your homework number 4. Okay, so we will have a number 3 when this Wednesday, right? Okay, the due date for homework number 3. After that, I'll give you a new one for 2 weeks. Try this one, but no worry. I know you are busy, so you have this code. But we have the TA have designed another interesting application. So I think you just have to go through all these content and then to understand how is this works for your restoration. Okay. Yeah. Any question on this winner filter design? Okay. It should be easy, right? Should be easy. No worry. I know you are busy and we'll give you easy one to do it, but the purpose is you have to understand why you do that one. Okay. I think we are going to continue chapter 6. Chapter 6.1. Oh, okay, thank you. Okay, so it's from image processing. I think the most important is the enhancement and restoration. So you have both content and also in frequency domain. You can do it in spatial domain. You can do it in frequency domain. And now we are going to change to the other issue. It's color image processing. Okay, it should be in the chapter 6 or chapter 7. So in this chapter, we have to understand the fundamental of the color and the color spectrum. Okay, you are going to see what's the color. Because previously, we only use a gray label image, right? You only have the gray label image to process. But now you know we all face the color image. So we have to understand the color component, how to do it in a better way. Okay, so we have to understand what's the color model. What's the color model? So I think you maybe just know the RGB color model, right? Right? So you know RGB color model. Have you ever heard about the CMY color model? CMY? Have you ever heard about CMY? Please raise your hand. Let me see. No? So do you know your printer? You are going to buy the printing cartridge. Can you buy the RGB cartridge? 彩色印表机 You are going to buy the cartridge, okay? Printing cartridge. Do you ever see cartridge, RGB? You know RGB color model, right? The red color, green color, and blue color. But have you ever buy the cartridge in red color, in blue color, in green color? No, right? Why? Because they are in different color system. Okay, we have two color system. One is active system. The other is a subtractive system. Actually, active is the most of time you use in your mobile phone and you're watching the TV. Okay, in the projection is an RGB system because it's light source. And then you have to use active to consider the color model. We call it primary color system. Okay, primary color model. But when you printing, when you drawing, it's different. It's different. We call it a secondary color model. Okay, secondary color system. So can you tell me, if your light, you know this LCD and there's a red light, yes, we can buy the blue light and the green light. If they add together, what it should become? It should be white light. Actually, it should be white light. You have evenly light source and then add together RGB color in your TV. They put out, you can see the white. It should be white color. But if you take the color, what's that? Pen drawing. Okay, if you have three different pen, okay, red color, blue color, and green color. If they draw together, okay, your water pen draw together. What the color should be like? In your experience, okay, I know you are not a painter, but if you experience, if you mix all this color together, break, right? So how come? There's some light, it become white, but when I draw in the three color mixed together, it become black. So it's got different color system. One is primary color, is active. The other one is subtractive, it's a secondary color system. Okay, so it depends your system. You use different color model. Okay, so RGB, the color model you should be very familiar because every day you look at your mobile phone. Okay, it's a LED system in your a monitor. Okay, the same. Your TV is a monitor. It's a light source. So when you put the light source out, mixed together, the RGB mixed together, it becomes white color. But when you use in the painting drawing system, the RGB mixed together, it's become black. But unfortunately, when you use all the color together, you cannot get a very black, true black. It's just become very dark, very dirty light, but it's not true black. So when you buy your printing cartridge system, CMY, we always have a black cartridge, So we have CMYK color model, extended color model. So yeah, but color model is trying to describe the color. Yeah, you are right. So can you tell me, if you see some handsome boy or beautiful girl and have a very good dress at the road, in the classroom, and you want to describe the lady who draw the maybe some red color clothes, how you describe it? Will you tell me it's the lady draw a red in 1200, green 175, and blue in 100? Will you describe like this one, this color model? You use RGB color model. Yeah, you tell me, because maybe she draw a brown color. So how can you tell me? You're going R equal to 20, G equal to 175, V equal to 30. Well, you cannot imagine it at all, right? What the color should be. So this color system is not convenient for our human communication. So there should be another better one. We call HSI color model. Okay, have you ever heard about this one? Or HSU, HSI. So it's a hue, saturation, intensity. Another color model. Hue is the 色调. You will say, oh, there's a sport car. It's a light blue sport car, shiny light blue sport car. You understand what kind of color I'm talking about, right? So I'm going to light. Intensity is low. Blue, light blue. Blue is the hue of the color. So it's another one. Hue, saturation. The saturation is what's the content of the white light mixed in layer. Okay, so you have a pink, you have a red, because they have different saturation level. Pink, red, dark red. They have mixed with a different level of white. So we use this one in our daily life. We don't use RGB in our communication, right? And you use some CMY to print your paper, to draw your pen, right? But so you have to know there are so many different color models. How about the communication for the TV? For TV, they didn't use HSI, they didn't use RGB, they didn't use the CMY, they used YIQ. YIQ color model. Because the Y is the true chromatic intensity level. So if this is the previous age. If you have a black and white TV, okay, so you are going to discard these two channels. But if you have the color television, you have to use these two to add up to this intensity level. So this is true gray level. Try for the communication. So they have different color model. So I think next time we are going to introduce all these different color model and how you transform from there, and how you make a good selection, and how they change to different representation. Okay, and even this CIE, the MOSFET color chromatic diagram, how you explain it, how you look at this the system. Okay, the balance. So there are different white color, equal spectrum there. Okay, so it's daylight, it's a cool white, it's a warm white, different white. Okay, even the white we have different. How you see that one? And we use this tongue shape. It's a CIE. It's called CIE diagram. It's a standard. Okay, CIE diagram. It's a chromatic diagram. And how we look at this one, and how we observe what kind of color you can. And actually, we have a blue here. We have a red here. We have a green here. So This is the color you can obtain from your TV only. A lot of color, you cannot observe it. And for the printing system, sorry, only part of it can be printed. Not all of them can be printed. So it's different color description in this CIE chromatic diagram. Okay, so we will give more introduction for the color image processing and how we do it, and maybe it become more interesting to look at this different color. This is YIQ transformation is different from RGB. They have different partial to transform to make it good for communication. Okay, so we will stop here for today's talk. And remember, Wednesday you have the homework sheet to turn in, and we will continue for the last homework. Okay, yeah. So class dismissed.